we talked about designers and foundry men working together. Okay, but now can we have work together to achieve a particular amount of cost reduction? Okay, and this is all about how much should you reduce and how do you reduce. I will be answering these two questions in this lesson. How much should you reduce and how do you reduce, what are the opportunities for cost reduction in a metal casting area. If you look at the 4 different stages or 4 different cost, you can say factors in a casting, you have the design cost, and you saw a big one, material cost in the last example. Then you have the labor cost and overheads. So design cost could be 5%, material cost could be 50%, labor cost could be 15%, overheads could be 30%. But the shadow by them, by shadow we mean the impact or influence by these 4 categories of costs are not the same. A designer who just draws with a pencil on paper or maybe a mouse on a computer screen, just by drawing a line and just by putting plus minus 0.05 millimeter, he has completely changed the way the part is going to be manufactured and what is going to be the cost of that. The influence of design on manufacturing, many people have said, is of the order of 70%, which is what you see here. On a shop floor, a labor guy, how much can you really influence? He is already constrained so much. Okay, whatever he does, a little bit here and there, I mean, you are not going to reduce cost much by his actions or whatever it is. Okay, material, if you are little substitute the material, maybe do some shape optimization or do something tricks, maybe you can do a little bit, but it's not that big. You are not too much leeway in material change anyway. You can change little bit, not too much. So the big thing or the big opportunity here is design. Conventionally, what you say, we say that my actual cost plus profits is equal to price. And what I do in a conventionally, I try to minimize my cost to the extent possible by not painting my machines and maybe hiring labor at a lower rate. Okay, I minimize my cost. The new approach is essentially called as target costing, where it's the same equation but I turned it around. Instead of saying cost plus profit is equal to price, I am now saying price minus profit is equal to cost, which means I first fix my price, I fix the profit I want to make on that part, and then I know I need to manufacture within that much of cost. That is the allowable cost. That's the basic change of philosophy, change of mindset, the change of culture, and change of way you do the manufacturing and costing and negotiation with customer. So in one line, the bottom line is important here. Here the goal is to set and achieve a specific level of cost reduction. I am not saying minimize cost. Minimize cost is a very vague target. Okay, I minimize 1 rupee also I minimized. But here you say no, you minimize a specific target and you achieve that and you say I have succeeded in that. Now very important slide, let's spend a little bit. The basic steps are like this. You start from the marketing department and marketing department says okay, the customer will pay this particular component or product at this price. You fix that first. Then you work back from the finance department, you ask okay, how much we have to pay distribution margin and taxes and all those things. You get those numbers and subtract that and you get your allowable cost. Then you go to the bottom step and say okay, if I make this part by my current techniques and current equipment and current manpower and current methods, what is cost going to be? You will find mostly that the current cost is more than the allowable cost. Allowable cost is 100 rupees, current cost is 120 rupees. So it could be more than that. If it's less, then there's no problem. Increase your profit margin. But usually it is the other way around. Then you fix the target cost in between these two. You say okay, allowable cost is 100 rupees, current cost is 120 rupees, you put target cost as 110 rupees. And say I'll reduce the cost by 10 rupees this year, next year I'll think about reducing by another 10 rupees. So you break up the reduction target. You break up the target as target cost reduction, which has to be done right now, and you say strategy cost reduction, which I'll do later, and until I do that, I'll take a hit on my profit. But it is only postponed, not cancelled. Okay, and then once you have the target cost for the entire product, you break it down into assembly and sub-assembly and component, and finally components to your even material and labor cost. Or if you're outsourcing that, you include a supplier team at this point of time. I guess Nano would have done that to achieve that 1 lakh car kind of a thing. Okay. So I have few slides on how do you calculate allowable cost and current cost. I think these are straightforward, I will not discuss that. And yeah, so these are the reductions. Let me give an example that will make it very clear. So let's say that the Mahindra did a market survey and found that in the north, which is real life here, there is a segment of farmers who can be tapped if we can sell a tractor to them at 3 lakh rupees. Okay. This is a nice market. It's a middle segment where it's a big body of farmers waiting to tap into this market. Then they went to finance and they said, okay, all these taxes and margins and freight, transport costs are, let us say, 57,000 rupees. Plus you also need to have warranty provision. In case some parts go wrong, you need to be able to replace that. It costs money, there is no free lunch, and let us say that is 3,000 rupees. So total 57 plus 3, 60,000 rupees is your provisions. I have slightly rounded up the number so it is easy for us to understand. Okay, I put all zeros on the last side. And then they say, okay, we want to make 10% profit margin, which is 30,000 rupees. So if you subtract from 3 lakh, 30 plus 60, 90, you get an allowable cost of 2.1 lakh rupees. Then you say that, then you go down to 9th step and you say that, okay, how much it will cost us if you do it by the current methods? It comes to 225,000 rupees, 2.25 lakhs. So there is a gap of what I want to achieve is 2.1 lakh, what I am able to do is 2.25 lakh rupees. There is a gap of 15,000 rupees there. Now I can't suddenly reduce 15,000 rupees just like that this year. So I say, okay, I do target cost reduction 10,000 this year and strategic next year, future 5,000 rupees. Okay, and then if I now take it forward to the next slide, my total target cost was 2.15 lakh, same number I am copying here, and then I put now some other addition numbers. What if my project fails? Let me have some safety margin. The reserve is a safety margin. I try to achieve little more cost reduction, so in case I fail, I still am within margins. That is my reserve. Then I have some additional equipment I am buying or additional people I am hiring. Okay, those are your development expenses, depreciation, additional facilities. All that comes to about 4 plus 8 plus 15,000 rupees. So if you have 2.15 lakhs is my target cost. I need to remove some more things, which is 4 plus 8 plus 5, which is how much? 12 plus 5, 17. So 2.15 minus 17,000, okay, comes to 1.98 lakh rupees. That is the final bottom line, my manufacturing cost. And then I say there are two aggregates. You say engine and then chassis or whatever. And you say, okay, chassis assembly is 1 lakh, engine aggregate is 98,000 rupees. And then you start, let's say aggregate 1, let's say your chassis 1 lakh rupees, you break it down into your either assemblies, assembly 1, assembly 2, that is already done. And within assembly you say component 1, component 2 and so on. In this case component 1 you are saying is about, let's say 1200. Then every component again you bring it down to material cost and conversion cost. So finally you will see that material cost for component 1, last but one row, is 920 rupees, conversion cost is 280 rupees, and that's really the target within which you have to manage that. Of course it is not that holy. Supposing you have two components, in one component you are exceed target by 10%, but if you are able to achieve the same thing, 10% reduction in other component, okay, you can always balance it across components like that. So overall that is the philosophy of target costing, and I am sure Nano would have tried that. Now important slide here. So where can we really save the cost in manufacturing, in casting? In manufacturing, two big places where you can save costs. One is trials. What we don't realize is that trials are not just remelting the metal. Okay, when you say trial, okay, it is not only tooling, modification, and your casting and inspection. That is what is commonly thought about. But what you're forgetting is that it's also lost opportunity. Those castings, that much time on the shop floor, that much you could do something else, that is also lost. And sometimes it is much more serious than that. Just because you are doing trials and then still trials and till trials, and then get a phone call from your customer saying, oh, don't bother about that, we already finalized with someone else, and then you lost the order completely. So I'm not even looking at those costs. I'm looking at just the cost of the tooling modification and melting and pouring and inspection. If you say for a normal medium complexity, medium size sand casting, the cost of these things is 20,000 per project or per trial, and I am saying you are doing only 2 trials, which I know is a much more underestimate. Real life it could be 4, 5, 6 trials. Many foundries are doing 10 trials and still going strong on trials over a period of time. And if you say you are developing a new casting, 1 new casting every week, again it's a small underestimate of that. You are talking about 20 lakhs lost per foundry per year. It is underestimated by sometimes a factor of even maybe not only 2 or 5, maybe by order of 10. It could be 2 crores per foundry per year lost, and not even accounting for the lost orders. The other big thing in manufacturing is the rejections. Again we think the rejection is, what is the rejection? Rejection casting, put it back into furnace, I'd only remelt that, I didn't lose anything. No, you lost, that casting should have gone in the truck and gotten you the money from the customer, and you are recycling. And you can also imagine recycling 100% of castings. You are spending a lot of money and not making money out of that. You can go into bankruptcy very fast. So a loss is also avoidable financial loss. If you even say that my foundry has currently 10% rejections and I reduce it just from 10 to 5%, and if I say that the price differential between a saleable casting and scrap is 20 rupees, again I am taking some average numbers, and other losses like transport warranty, maybe 10 is too much, but you can say total is 30, should be a reasonable number. You are talking about 1500 rupees per ton lost per foundry. Both these are avoidable losses. And if you see what I didn't put here, we did that per all the, we know there are 5,000 foundries in the country, we know there are total production is 7.5 million tons. If you multiply 20 into 5,000 foundries and 1500 ton into 7.5 million tons, it comes to about 3 to 5,000 crores per year. That's what I said is an avoidable loss in the country. So that should give us maybe some more ideas to push the government and tell them, hey, we will save that much money to the country. More than that, we are also talking about energy efficiency and pollution. All this will come down if you, at least by few percentages if you do that. Now we'll speak about what are the opportunities in cost reduction by design. Okay. And a few examples, again we converted from 2D to 3D to illustrate it better. You see the first example, the parting line being stepped, and if you can just move the left feature to a little bit down, so I can have both the flanges in one line, and therefore I can have a flat parting line. Oh, wonderful! I mean, I can reduce my tooling cost at least by 5-10%. Okay. Similarly, the second example, left on the bottom, you see the 2 ribs on the top are, we need an additional core because there's an undercut. I move the rib to the middle. Oh, I don't have an additional core. Again, reduction by few percentage in tooling cost. Similar example on the bottom right one. Okay. Some more, I'll make an example slightly more and more complex. On the left example, if you see, you need a step core. Okay. I made a little more simplified core. On the right side, you see there is an undercut on the outside, so you need an additional core on the outside top. That is eliminated by making it straight. So you have single core from inside only. Of course, you might have mass concentration on the thick wall around that, but it is not difficult to feed. Okay. And some more examples from ASM book now, and 3D. Okay, ASM book is 2D, here it is 3D. You see core, if you have a step like that, undercut there, and you may need either 1 core or 2 cores depending on how you want to make that. Okay, but if you just make the step, remove the undercut there, you can make it without any cores at all. 0 cores here. 1 core or 2 cores to 0 cores is a big improvement. Here, because those side ribs are there, you need a complicated core, which is not complicated, but it's a big core which goes all around the casting. And that can be pretty expensive because you need a big core box to make that big core, and then handling of the core, and then placing it and all that. If only you remove the ribs by some method, or you can even put them inside if you want. Anyway, I need an inside core. I can combine both into a single feature there. Okay. Look at now this example. You have 3 cores, and the 3 cores you can see in the bottom left picture where the 3 cores are coming from. And if you can just change the part design from the left design to right design, you have reduced from 3 cores to 1 core. Your tooling volume, core volume, number of cores comes down by 2/3 to 1/3. Little more trickier example. You have to recognize what is the problem in the left picture and how the right side presents a solution for that. Okay. By doing this, we are reducing now from 2 cores again to 1 core, and the core volume also to half the core volume. So core material recycling, all those costs also come down. Okay, last example here. The part looks very innocent on the left side, right, left top, but actually to make it you need how many cores? Okay, all those cores can be reduced. Okay, this is the first initial thing, and now by redesigning the part little bit, you are now reduced to only 3 cores. Maybe there are about 7-8 cores, reduced to 3 cores. Core volume also reduced to one half. Okay, one more example here. Again 3 cores here. I'm redesigning the part. Now you have just one simple straight middle core and then one around the core. It's not so great. You still need a big core on the outside. If you can reduce that also, nothing like it. Okay. So what we've shown you are some few examples of how to reduce the tooling costs, which is driven directly from the part design. Okay. And these can be significant, especially when the order size is small, like the one we were talking about little before. So if you want a small order size of a complex shape casting, the maximum worry you have to worry about is tooling cost. Because tooling manufacturing time and tooling cost both get affected if your part shape complexity is very high, and you are producing too many cores. Each core adds to time and cost of my production. And the other one we talked about before that was how to reduce manufacturing cost by reducing the number of trials on shop floor. If you can get the casting right with just one trial on the shop floor, life is very good. And secondly, if I can reduce my rejections from whatever I am to, let's say, target to half of that in the next 2 years, and then target to half of that in the next 2 years, and keep going that, if you can reach to below 1% in 5 years, 10 years time, fantastic, for jobbing orders, okay, not for regular production of the same part. If you can do that, it's great, and then that's the road to go towards ppm level rejections. Okay, that's in a nutshell is about perfect castings, where we talked about perfect castings where you are giving the quality that the customer wants at the low cost of frugality that a foundry desires to be able to have best of both worlds. So in a sense, we have wrapped up the whole discussion on quality and frugality by design. The whole point is to move it to design parameters which can be easily controlled, and not manufacturing parameters which are anyway too many and uncontrollable. Make the designs more robust. Okay.